The physical record of an aircraft wreck usually reflects the kinetic forces of its final moments. The remains of the Martin B-26 Marauder bearing serial number 401370 dictate a completely different procedural reality. Later known to restorers and aviation historians as basket case, this early short-wing bomber does not present a standard crash debris field. The primary constraint governing recovery was not impact damage alone. Wartime stripping, disposal, and later handling had broken the bomber's structural continuity long before restoration was considered, leaving a partial, disconnected aluminum shell that had to be recovered and stabilized before it could ever become a displayable, structurally sound airframe. This structural disruption overrides normal engineering logic. An aircraft relies on continuous load paths to maintain its shape and support its mass. The early Marauder uses a stress skin, semi-monocoque style structure in which the exterior metal skin works with frames, bulkheads, stringers, and spars to carry loads. With those members missing or distorted, the shell could no longer be treated as a reliable load-bearing object. Unsupported skin, broken bracing, and severed wing roots made the remaining pieces vulnerable to deformation and secondary collapse. That loss of continuity creates the next handling problem. The center of gravity shifts unpredictably. Engineers attempting to lift or secure the wreckage cannot rely on factory hoist points. Those lifting points are either missing or disconnected from the main mass of the fuselage. The surviving aluminum skin must carry handling loads it was never designed to bear. This makes the physical recovery of a cannibalized bomber exceptionally difficult. The salvage crews prioritized immediate military necessity over preservation. They left behind a structural puzzle lacking its most critical connecting pieces. The remains of basket case experienced this exact procedural dismantling. The mechanical severing of the airframe ensured that any future attempt to move the remains would risk further tearing of the weakened metal. Because the active airfield required clear aprons for ongoing military operations, the dismantled fuselage and severed wing sections were forced off the working surface and into an earthen gully adjacent to the Naknek Army airfield. This dump site served as a purely functional disposal area for ruined hardware. Pushing a structurally compromised shell into a gully induces further deformation. The deliberate mechanical cutting permanently altered the geometry of the airframe before it ever settled into the dirt. How did the aircraft end up in the dump site in the first place? The aerodynamic geometry of the early Martin Marauder imposes a severe operational constraint during the landing phase. The short wingspan of this specific variant produces high wing loading, and that high loading gave the type a reputation for demanding high approach speeds. Contemporary and later accounts cite different figures depending on weight, configuration, and source, but the operational point remains the same. The aircraft could not be treated like a slow, forgiving trainer on final approach. That translated into a narrow energy margin, enough speed to avoid a stall on final, but once the wheels touched down, the tires and brakes had to absorb the remaining kinetic energy within the available runway length. On a paved dry surface, this energy transfer is a calculated engineering baseline. On a semi-prepared muddy strip, the high-speed landing regime sharply reduced the margin for error, operating as part of the 73rd Bombardment Squadron in the 11th Air Force. This bomber served in the unforgiving Aleutian theater. The operational environment forced crews to rely on primitive runways while conducting critical patrol, defense, and transport movements across Alaska and the Aleutians. Sources agree that on August 16, 1942, the aircraft was lost while landing at Naknek, also associated in records with King Salmon. The sortie context is less secure, with some accounts describing the loss after patrol operations and others identifying the flight as a ferry movement from Elmendorf toward Naknek and King Salmon. The approach was flown in bad weather and under difficult field conditions. The landing ended in a runway departure at Naknek, with the bomber skidding off the prepared surface. The available published accounts support the basic sequence of a hard landing or loss of control on landing, but they do not establish a precise touchdown speed, the exact depth of mud, or a detailed tire friction mechanism. During such a departure, the landing gear struts could endure massive lateral side loads they were never engineered to survive. The runway departure and collapse damaged the forward fuselage and nose structure. At least one crewman, Staff Sergeant William W. Chapman, was killed in the crash, and some records report 2 fatalities among the crew. The kinetic energy of the accident left the forward airframe damaged badly enough that the bomber was declared a total loss rather than repaired for service. The physical record then entered a long phase of environmental decay. The aluminum structure remained at or near the Alaskan airfield dump for decades, before recovery in the year 2000. Public reporting does not fully document the exact exposure pattern, but the preservation problem is clear. Aircraft aluminum alloys are engineered for service lives that include inspection, cleaning, drainage, coating repair, and corrosion control. Once a damaged airframe is left in direct contact with soil, standing moisture, and subarctic weather, that maintenance system disappears. During the subarctic summer ground, moisture can seep into shattered skin seams and pool inside lower fuselage structures. The protective coatings on the metal were already compromised by crash forces, stripping, and later handling. When temperatures fall, trapped water can freeze and expand, stressing rivets, seams, and panel joints. Year after year, that thermal cycling can enlarge existing damage rather than create a clean and readable wreck. Simultaneously, damp earth can accelerate corrosion on exposed metal surfaces. Wet soil can act as an electrolyte and promote localized attack on aluminum structures, especially where coatings are broken and dissimilar metals remain in contact. The lower fuselage sections resting in the mud would be expected to lose stiffness, while exposed upper surfaces would remain vulnerable to wind, temperature swings, and mechanical damage. The combination of initial crash forces and long environmental exposure fundamentally compromised the surviving structural integrity of the airframe. What structural integrity remained after decades of Alaskan exposure? The physical assessment of the Naknek debris field presents a stark contradiction in material survival. Surveying the wreckage reveals that the main crew compartment remains highly recognizable, while the lateral lift structures are virtually non-existent. Before any physical handling, investigators had to map the surviving structural members against the voids left by salvage and decay, categorizing the debris by what remained structurally viable rather than by what the bomber had once been. The main body was the strongest surviving portion of the aircraft. Restoration reporting has estimated that about 80% of serial number 40-1370's fuselage survived, though that figure should be treated as an estimate rather than a formal survey statistic. Finding that much original fuselage material is significant for an airframe subjected to crash damage, stripping, dumping, and decades of Alaskan exposure. Material survival did not equal strength. The forward fuselage remained heavily compromised, with lower surface crushing, warped bulkheads and frames, disrupted datum lines, buckled skin panels, and damaged seams marking the boundary between recoverable structure and metal too distorted or brittle to trust. Before the section could carry any display or handling load, it required repair rather than simple realignment. Moving outward from the central fuselage, the material contradiction becomes undeniable. Restoration reporting has estimated that only about 30% of the wing material in the final project would be original. That absence of original wing structure dictates the physical limits of the wreckage. The wing material that survived was badly damaged and cut up, with published accounts linking at least some of that cutting to recovery history rather than proving that every severed member was cut by wartime maintenance crews. Every surviving wing fragment must be individually tagged and mapped in relation to the main body. The surveyors record the orientation, fracture patterns, and cut edges of the debris so the recovery and restoration teams do not confuse crash damage, later handling damage, and deliberate cutting. The condition of the severed edges provides boundaries for what can be saved. Meanwhile, mapping the fuselage mass requires identifying the exact points where crushing terminates and viable metal begins. This distinct separation of evidence ensures that the final inventory is based on measured physical reality rather than optimistic assumptions about the surviving shape. The assessment confirmed that the surviving wing fragments were disconnected pieces rather than continuous load-bearing assemblies, so they could not simply be bolted back to the fuselage and trusted as structural members. This disparity became the static reality that governed movement planning. A substantially surviving but heavily damaged fuselage remained beside a severe void in the wing geometry, leaving the original wing material useful for history and limited reference but requiring much of the final wing structure to be repaired or fabricated before any logistical move could be planned. A heavily crushed fuselage shell lacking rigid wing roots to stabilize its center of mass is highly unpredictable. The remaining connections between the buckled frames and torn skin panels are exceptionally fragile. The immediate operational challenge requires determining if a wreckage field this compromised could be safely extracted from the tundra without further fragmentation. In the year 2000, the Aerospace Heritage Foundation of Utah opened a narrow logistical window, launching a physical recovery operation to extract the Marauder from the Naknek Gully. Every physical interaction required deliberate constraint management to avoid turning the recovery itself into another destructive event. Extraction from the remote Alaskan site could not rely on standard lifting assumptions because the internal bulkheads, wing roots, and fuselage load paths were no longer intact. During later transport, the components still had to be secured against road vibration, shock loads, and shifting weight that could turn old crash damage into fresh fractures. The documented result was the successful removal of the damaged airframe from the Naknek and King Salmon area and its transfer to Hill Air Force Base in Utah. The sling, cradle, excavation, and transport sequence remains unpublished. This relocation changed the preservation context, but the exact storage conditions are reported differently in later sources. Some accounts describe long-term holding with little restoration progress, while another notes outdoor storage awaiting restoration. What can be stated safely is that the bomber remained unrestored for many years after recovery, and the primary structural deficit remained unsolved. The fuselage was still heavily crushed and structurally disconnected. Even in storage, the weakened shell needed support to prevent sagging or fresh damage. The museum possessed the historical artifact, but without the components and engineering resources needed to bridge the severed load paths, the bomber entered a long holding period until a verified physical solution could become available. By the mid-2010s, that unresolved challenge had become a decision about final physical form, whether a disconnected shell could be engineered to support its own weight again. The wreckage passed into the hands of Pat Rogers and aircraft restoration services in the California restoration world, with published sources placing the transition around 2015 to 2016. This shift moved the operational focus from long-term holding to active problem-solving. Upon uncrating the components, the engineering team executed a comprehensive physical audit of the surviving aluminum. That audit isolated the obstacle. The forward fuselage of 401370 retained its historical identity, but lacked a structural center of gravity anchor. Without the massive central wing spars and the heavy bomb bay bulkheads, the forward shell was essentially a detached hollow cone. It possessed no geometric foundation to mount a forward landing gear or to bear the cantilevered weight of a tail assembly. Attempting to bolt newly fabricated internal framing directly to the heavily compromised 70-year-old skin panels would induce localized stress fractures. The ancient aluminum was too brittle to accept the required load transfers. The engineering team concluded that a traditional single airframe restoration was physically impossible. The restoration team answered with composite restoration logic. When one artifact lacks continuous geometry, major structural nodes from other airframes can restore physical viability at the cost of singular historical purity. Aircraft restoration services formalized a blueprint using major components from 3 known Marauder sources. They established the damaged forward fuselage of serial number 40-1370 as the central identity of the build. To resolve the massive void located directly behind the flight deck, they acquired the center bomb bay section of another Marauder, serial number 40-1381. This second bomber had also crashed at the Naknek field on August 16, 1942. While its own forward and aft extremities were not the answer to this project, its bomb bay section retained the heavy structural geometry needed to serve as the core of a rebuilt fuselage. To finalize the complex curves of the extreme forward geometry, they used a cockpit section believed to come from serial number 41-31748, a surviving section with a different later history rather than a fully documented third Naknek wreck. The bomb bay section supplied the structural keystone, the reinforced box where the wings attach and where forward and aft loads converge, giving the engineers a solid anchor point. The direct structural splice would align the surviving longitudinal stringers of the primary fuselage with the heavy bulkheads of the new center section, routing handling and display loads into the rigid bomb bay node so the compromised forward skin could hold its aerodynamic shape rather than carry the aircraft's static weight. Using 3 distinct airframes gave the team the geometry needed to attempt a stabilized bomber. The remaining problem was how to merge those wrecks into a single load-bearing fuselage without destroying the original surviving metal. Physical merging began by stabilizing the forward fuselage and removing metal that was too distorted, missing, or structurally unsafe. Published restoration reporting confirms extensive structural work and fabrication, but not a public step-by-step shop log of every rivet, bulkhead, splice plate, or fastener. The safe description is that damaged material was repaired or replaced where necessary and aligned to a rebuilt structural foundation, while preserving as much original skin and identity-bearing material as possible. With the forward fuselage stabilized, the engineering team entered the alignment phase, where separate aircraft components had to become one cohesive unit. The repaired forward section had to be aligned with the heavy bomb bay section of the second Naknek wreck. This mating process demands exact geometric tolerance across multiple axes. The engineering crew must match the longitudinal datum lines of both massive sections before committing to a permanent join. If the 2 components are misaligned during the initial join, the resulting airframe can be twisted and structurally unreliable. The publicly available sources support that broad strategy, but they do not confirm the exact unpublished shop sequence of drilling, clamping, fastening, or splice plate installation. The intended splice was to carry the suspended weight of the forward section into the solid foundation of the center node. After alignment, the safer conclusion is narrower. The public record supports an active composite rebuild using the major components, aimed at a stable display airframe, not a confirmed finished aircraft standing on its own landing gear. The outcome remains an ambitious structural rescue centered on serial number 40-1370, with the degraded Naknek fragments folded into a composite rebuild still reported in the aircraft restoration services world and aimed at a display-capable Marauder. If completed as planned, the stabilized bomber will preserve a rare physical record of the Aleutian campaign and the severe mechanical constraints faced by the 11th Air Force.